to 300 PFC. PFC is parallel flame channels are welded toe to toe as shown to form. So there is a one channel, second channel, and they are welded to compound box section. So it is a box section square for a concentrically loaded columns. The effective length of the buckling about both section axis is 6 meters. Determining the design capacity of this compound column and compare this with the design capacity of the single 300 PFC with the same effective length. So we first need to find the capacity of this double channel. First find the capacity of these double channels, and then we're going to find the capacity of the single channels, and we're going to compare both. So let's start with the double channel first. So this is the first one and the second one and welded together. So we first find some information from the one steel tables, the gross area for single channels. So from the one steel tables here on page number 19, we have a 300 PFC parallel flame channels. In that one, gross area is given 5110 millimeters square. So that is 5100 millimeters square, and that's times by 2 because we have two channels. That's give us this number. The moment of inertia about the x-axis, 300 PFC, moment of inertia about the x-axis is 72.4 times 10 to the power 6, and there is a two channels. So this value is given for single channels. Now we have two channels, so that I multiply by 2, that gives these numbers. Radius of gyration about the x-axis, 300 PFC, our x value is 119 millimeters. So that is radius of gyration about this x-axis. Now we need to find the moment of inertia about y-axis. We found the moment of inertia about x-axis, but we need to find moment of inertia about y-axis. Now in this 300 PFC, it has given moment of inertia about the y-axis, that is 4.04 times 10 to the power 6, but that is for single channels. We need to find for double channels. So for that one, we need to multiply 2 because we have two channels. 4.04 times 10 to the power 6, that is single channels, that is taken from here. 404 times 10 to the power 6 taken from here. 4.04 times 10 to the power 6 for IY, plus area 5110, that's the area 5110 times 90. 90 is the width of this flange, that is given here, 90 width of the flange. Take away 27.2, that is 27.2 is taken from here, coordinate of the centroid in the x. So x 27.2, that is the coordinate centroid coordinates from 27.2, that's square. That's give us 48.4 times 10 to the power 6 millimeter power 4 for IY. Gross area is 5110 millimeter square from one steel tables. Now radius of gyration about y-axis, in the one steel tables it also given ry value, but this ry value, which is 28.1, is for single channels. We need for double channels. So the IY value for double channels over area of the double channels, so 48.4 times 10 to the power 6 that we calculated, over the gross area that we calculated 10,220, so that is 10,220, 68.8 millimeters square. Since the effective length for the buckling is the same about both axes, and Ry, which is 68.8, is less than Rx, so Rx is 119, buckling will take place about the weak y-axis. So y-axis is weak, so you can see this y-axis is a weak axis, the buckling takes place about the y-axis. Kf is 1, that is taken from one steel table. So on same page number 19, 300 PFS, form factor Kf is taken 1. Modify compression member slenderness, lambda ny, as the y is the weak axis, so we need to find lambda ny. So that lambda ny equation is taken from here on page number 84. We on the AS4100 we have these big equations. Now on that equations we found this lambda n, Le over Ry, length, effective length, that is given in the questions. Length of the length is given 6 meters in the question, so that is 6,000. Ry we calculated 68.8. Form factors we get it from one steel tables, times the yield strength 300. From the one steel table 300 PFC, we have two yield strength given, Fy for flange and Fy for web. So we just taking the minimum of 300 and 320, so 300 megapascals. So that is 300 megapascals over 250 gives a 95. Now member section constant alpha b is 0.5, that is coming from table table 6.3.31 on page number 85. We have two tables, one for kf equal to 1 and kf less than 1. In our case, the kf value that we found is kf is 1, so we must use the table 6.3.31 which has a kf equal to 1. In this one, compression member section constant lambda b value is given for different cross sections. So in here we can find the hot roll channels. That's hot roll channels has a alpha b value 0.5. So alpha b is 0.5. Now member slenderness reduction factor alpha c. Now that alpha c value is given on page number 86. It has a slenderness reduction factor alpha c for lambda n. In our case, lambda n we found 95 and we found alpha b 0.5. So alpha b 0.5 and 95. So 95 and for alpha b 0.5 we have 0.515 that is taken here, 0.515. Now nominal section capacity, again that equation is given in the standard on the page number 81, close 6.2.1. The equation is given. Kf is 1. We found Kf equal to 1 from one steel table. Gross area 10220 that we found for the gross area for two channels 10220 millimeter square, and yield strength 300 that is coming from one steel table 300 PFC. We have 300, 320. We take the minimum value 300. This multiplication gives this big number, divide by thousands, that gives 3066 kilonewton. Now nominal member capacity NC, that equation is given on page number 83, close 6.3.3. Equation is given. So alpha c times ns, we calculate alpha c 0.515 times the section capacity 3066, give us 1579 kilonewtons. Multiply with the capacity factors 0.9, give us 1429. So that's the capacity of the double channels. Now we also asked to compare this capacity with the single channel. So we are taking the single channels 300 PFC. Then in that case we need to calculate the modified compression members. That equation is coming from page number 84. Lambda n value is taken from here. Now we're going to repeat the whole procedures again for single channels. So I'm just going to quickly run through these values. So 6000 is the length of the channel, so that is taken from the questions. 28.1 is the RY value that we can extract it from the one steel tables. For the single channel 300 PFC, RY value is 28.1. So that is 28.1. KF is 1 and 300 is taken from 300 PFC. That is between 300 and 320, 300. I'm using these equations from here. I did not write that equations, but that equation is L over RY KF FY on 250. That is written here. So that's give us 234 lambda n. Now member selection constant alpha b, KF value is still same. So in that case, same like double channel 6.331 KF equal to 1, we can take alpha b equal to 0.5 for hot roll channels. Member slenderness reduction factor alpha c for lambda n 234 and alpha b 0.5. So in the tables on page number 87, we have a lambda n 234, so it falls between 230 and 235, and alpha b is 0.131 and 126, that is written here. So 230 has a 0.131, 234 we need to find, that's I put x, and 235 we have 0.126. So we need to do the interpolations. Interpolation is 235 take away 230 respectively 0.126 take away 0.131 equal to 234 take away 230 x take away 0.131. Simplification gives the value lambda n 0.127. Now nominal section capacity NS coming from Australian standard, that is on the page number 81, NS KF AN FY, and that's KF is 1. We can take it from the one steel tables 300 PFC, KF equal to 1. 5110 is the gross area. So 300 PFC, gross area is 5110. Now we are taking for the single channel, so we don't need to multiply by 2 times the yield strength 300. That is 300 PFC has a 300 and 320 yield strength, so 300 yield strength. So that's give us big number, divide by 1000 to get kilonewtons. Now nominal member capacity alpha C, that equation is taken from page number 83 on clause 6.3.3. NC value, NC equation is given. So alpha C, we calculated alpha C 0.127, section capacity we calculated 15300, multiplication gives 194 kilonewtons, multiply by the capacity factor 0.9 give us 175 kilonewtons, so that is 175. Now we are going to compare two values which we calculated 1421 for the double and the single one is 175. So let's do the comparison. So comparison for single channel and double channel. For single 300 PFC and this is double, we welded these two channels by the welding. So capacity is 175 kilonewtons for the single channels we found. For double channel we found, for double channels we found 1421 kilonewtons. 1421 kilonewtons. So single channel capacity divided by double channel, so 175 divided by 141 times by 100 to get the percentage, so 12%. So I can say that capacity of the single channel is 12% of the capacity of the double channels. Thank you very much.